an arrogant ass about everything that deals with Amazon. When we have problems, I say, well, it's because like nobody else has a server farm quite the size of us. This is not true of Datadog. I think Datadog actually has an infrastructure that is larger and more impressive than Sharpie. So basically, anything that they ever say, I make sure to listen. So Doug will be talking about how they scale out their analytics platform. So thank you.
Hello, everyone. Let's get started. With all apologies to Darwin, I want to start off by giving you a brief theory on the evolution of a data project. If you've ever worked with data, you've probably done a project that started out really small. Maybe you need to move some data from one application to another. It just needs to happen once a day. So you start off with a Python script. In my experience, this is sort of the gateway drug of data engineering. It's really easy to get started. So you write your Python script, you pull a little data out of the first database, you put it into the second database, maybe some light transformation. You put it in production and it runs really fast, maybe like an hour, everything's done. So this is great, but then a terrible thing happens. Your business is actually successful. And before you know it, you're collecting more and more data, and the Python script that used to run in like an hour is taking 2 hours, then 3 hours, and then the sun is rising and your Python is still cranking. By a show of hands, has anyone ever written this script, the little Python script that couldn't? Right. So in my experience, the next step is you look around and you say, aha, we have this database where we were pulling data out of. Why don't we just move our computation over there? We won't have to move any of the data out. It'll be really fast. So you rewrite it as SQL, you move it into the live database, and it's amazing. It's fast again. But then you hit the next problem, which is that it turns out there was an application running on that database, and it turns out that it doesn't like you doing enormous sequential scans of its data tables. It grinds to a halt. People aren't very happy. So very quickly, you reach the next step in evolution, which is moving your computation over to a reporting database that you replicate from the live DB. So things are pretty good. Usually for a while here, you have a sort of paradise all to yourself to do enormous reads. But then eventually the data keeps growing. More people find your reporting database, want to do their own things. And before you know it, you're buying a bigger database, and then a bigger database, and then a bigger database than that. And eventually you've got the biggest, baddest reporting database that anybody can buy. And then we hit a phase of evolution that is really, really no fun. You've reached the ceiling of the scalability on a vertical database, and there's really nowhere to go. Fortunately, 10 years ago, this would have been the state where you have to stay, but now it's not the case. In 2016, if you look around, you probably have a Hadoop cluster or a Spark cluster that someone set up, or if you don't, you can get a hold of one. If you move your computation over to Spark or over to Pig or Hive, you're going to be able to scale it horizontally, and things are going to be good again. This is really nice, and in my experience, it not only follows the evolution of a small data project, but also our evolution of data engineering as we've gone. But what I want to talk about today is how I think this state of having one big Hadoop cluster where we do all our work is not the end of our evolution. Rather, I think there are some things that, that we've seen that need fixing with this. The first of them is that with a single cluster, your data winds up locked in. It's very, very hard to get at it from all the other places that you'd like to use data, and even more so, it becomes a victim of its own success. So you have this big cluster, and everyone realizes that they can take their slow Python script and move it onto the cluster. So before you know it, you can't get the time you need to do your work. Everyone's waiting around, be it humans trying to run jobs or automated jobs trying to run. And paradoxically, you wind up also with a state where when everyone leaves for the night or on the weekends when nothing's running, the clusters are super underutilized and you have all of this expensive hardware sitting around. So it's a sort of strange thing where you can't get at the data outside the cluster. The cluster's very, very loaded during the day and you can't get time on it, and then you have expensive hardware that you're wasting. At Datadog, we've built a platform that addresses these concerns. And specifically, we focused on the first word there, elastic, making it so that it can grow and shrink as we need and sort of throughout the day and throughout the week. So I'm going to talk today about the parts of that platform. My hope is that there'll be things that we did and learned that'll be useful for you all. So by way of introduction, I'm Doug. I'm Director of Engineering at Datadog. I work on these data systems and a lot of other ones. If you're not familiar with Datadog, we're a monitoring service for large-scale cloud applications. So I'm talking today specifically about our big data platform, and it's mostly focused on things like Hadoop and Spark. Its main consumers are data engineers and data scientists, the sort of people that come to this conference, particularly our internal ones who are trying to do work on it. And the stuff we're doing is actually rather various. We, first and foremost, are building features that ship directly to our main application. Anything that can really emit of higher latency than sort of a few seconds. So things that can take an hour and it's okay, those things are going on Spark and Hadoop. We're also doing a ton of statistical analysis. So things like outlier detection, machine learning, a lot of anomaly detection is going on. And then we use the platform for any sort of questions we have about how the data is structured or usage patterns in the data. Our main tooling for that at this point is Spark. We've switched everything new that we do over to Spark, and we're really loving it. We also use Zeppelin for a lot of the ad hoc investigation. Traditionally, we used Pig, and we still have a lot of stuff running. It's a real workhorse for us. And then we use Luigi, which was mentioned in the Spotify talk yesterday as our workflow tool for sort of coordinating everything. I'll talk about how a lot of these work later on in the talk. As a guide to both the talk and to our platform, I'll take it in three sort of sections. The first is cloud storage, which we find underlies everything for elasticity. And the second is the compute that we layer on top of that, which is also highly elastic. And finally, a very, very essential part of this is all of the tooling that we have around the edges that makes it possible to run with such dynamism. We'll start out, though, first with cloud storage, which underlies everything. This part of the talk could probably be called Amazon S3, a song of love. So before we talk about how we store the data, let's talk a little bit about what we're actually putting in there. So I mentioned that we're a monitoring service for large-scale cloud applications. We have over 150 different integrations from all sorts of things, web services, databases, queuing systems, pretty much anything that people use to run modern software, we're collecting monitoring data from it. And so we collect several different types of data out of this, but by far the largest and the most important is time series data. So for a brief primer as to what time series data is, this is a graph of, say, the idleness of a system CPU. And so you can see, it sort of fluctuates a little bit as time goes by. That little dot there is a time series data point. So a little snapshot of that on the right. It's a pretty simple data type. It has a timestamp. It tells you when you took the measurement. That's just a Unix epoch up there. It's got a metric, which tells you what you're actually measuring. Here it's the system CPU idle. It could be the number of requests to your web server. It could be quite about anything. Then the value, which is the measurement that you've actually taken. And finally, the tags, which give you context for that measurement. So it was on this particular host. That happens to be a Cassandra host. Maybe it's in this availability zone. Anything that you want there. So what you'll notice is that this is a very small data type. There's not much data in each of these points. But we're collecting over 1 trillion of these a day at this point, and it's growing very, very fast. So all of that data needs a home. And for us, the answer is Amazon S3. So I'll tell you first a little bit about how we actually get our data into S3. And so this architecture focuses specifically on the big data part of what we do. There's also a very extensive real-time architecture. But for this part, all the data is being ingested into Kafka, which is our distributed real-time message queue. And then we have a consumer, actually a set of consumers that are written in Go, that are actually buffering this data to disk into sort of manageable chunks, occasionally sorting and deduping it, and then uploading it to Amazon S3 in an internal format that we store. This format is optimized for a few things that we do outside of the big data platform. From there, we actually suck that data back down using Luigi and a combination of Spark and Pig jobs, and we rewrite it back as Apache Parquet. There's a talk later on Parquet, and I highly recommend it as a format. It's very, very nice. It's a columnar data format that compresses very well, and we use it for as much of our big data as we can. And then finally, we're writing over to a Hive metastore that's telling us where to find the data on S3. It's sort of like a map to what we're storing there. So that's what we're doing. So one thing you might notice is that there's no HDFS anywhere on that diagram. This is a data engineering conference, so you all are probably pretty familiar with HDFS, but it's the storage system that backs Hadoop. It's rock solid. Everyone uses it. It's really great. So why aren't we using it? Well, there are a couple things that we don't really love about HDFS. The first is that it locks you into one cluster. all of the storage is only accessible to jobs that are running in the cluster where you put it. And this doesn't sound like a huge problem at first blush, but you'll see in a bit all the things that we're doing because we don't have to deal with that. The second thing is that we actually really just wanted to store some data. We didn't want to run a bunch of servers to do it. So servers have CPU, they have RAM, they go down. All we really wanted was some bytes to get stored somewhere. And finally, HDFS is a Java JVM fiefdom. If you're coming at it from languages that aren't JVM languages, you're going to find that it's a very, very hard time to get your data. It's possible, but it's not the main use case. On the other hand, S3 is super flexible. So the main point about it is that once you have your data in S3, you can actually point any number of clusters you want at it and read it through a file system. This is crucial to the work that we do. Next, you can pretty much put as much as you want in there, and there's no management at all. All you need to do is make sure that you pay your credit card bill at the end of the month, and the storage is going to keep coming. And it's actually rather inexpensive compared with the cost of running servers to do that storage. And this is totally insane. That's the real durability number, which is 11 nines. To put that in context, if you store 10,000 objects on Amazon S3, they expect to lose one maybe every 10 million years or so. That's really, really amazing. The availability is also quite good in practice. It hardly ever goes down. And finally, any programming language that you're using that's been around for more than 10 minutes has a library for Amazon S3. And if it's been around for 30 minutes, it's probably a good library for S3. So from Go, from Python, whatever we're doing, it's great. So you may be thinking, one of the received wisdoms of data engineering is that you should put your data with your compute so that it's very fast to do your compute. This was sort of the innovation of the MapReduce paper and a lot of other things. So why would we put our data in a networked file system and separate it from the compute? I want to say that the received wisdom of how to do this isn't wrong. It's just that we went a little too far with it. There's a happy balance that you can strike. So breaking the rules is actually not so bad, and I'll show you why. This is a snapshot of a pig job that we run. It's a rather large job, and this is from Lipstick, which visualizes it. So these highlighted parts, which are, each of these is a MapReduce job that Pig has written. These are the only parts where we're actually touching Amazon S3. The first up top where we're loading the data, and the second down at the bottom where we're writing it out. Everything that's happening on the intermediate there is actually happening in HDFS and is happening on local disk. So really, the points where we hit S3 in a given job are actually rather small. So this additional cost, in benchmarks, it's roughly 2x. Getting to S3 versus getting to HDFS depends quite a lot on the instance type you use. But it's amortized over this entire long job that's hardly ever using S3. So in reality, it's not that bad to use S3. The flexibility that it gives you, you hardly pay for in performance. So once we have this base layer of cloud storage, we can do some really cool things on top of it with elastic computing. So the way this usually works, if you're coming from a non-cloud environment, is that you have one enormous cluster. And pardon me here, I'm sort of mixing my metaphors a bit, but it's basically the Death Star to rule them all. We do something very different. This is a snapshot of a host map of our clusters from just a given time during the day. You can see that we have many, many different clusters running of varied sizes. Pretty much every new automated job that we do launches its own cluster. Also, every data scientist or data engineer can have their own cluster or multiple clusters, however many they need. It's usually about 10 to 20 at a time, and node counts are very sort of unscientific because we run different types of nodes, but you know, it's in the hundreds of nodes at peak, and it can go down to almost nothing when nothing is running. And I did a calculation over the last month, and roughly 2 hours is about the median lifetime of the clusters we use. And so you might ask, why would we do this? Why would we run all of these clusters instead of just having a single Hadoop cluster the way many people do? There are some really good reasons for it. The first reason is that we know exactly what's going on any cluster at any time. So this is an example of a job that we launched. You can see up here, this is the number of yarn containers pending. That's basically the amount of work that's to be done on a given cluster. You can see we launched the job there, it spikes up, and then it slowly starts going down as we accomplish tasks. we can look at what's going on across the rest of the cluster and see exactly what our constraints are. So for instance, on the right here, that's the disk that's in use. You can see as we start running, we're slowly eating up disk. We don't have a problem where we're doing something like exponential, writing a ton of extra disk, and we're going to have problems. We can see the CPU on all of the hosts on our cluster. This is a heat map, so the parts that are darkest are where most of the machines cluster. As soon as we launch the job, we hit the ceiling. We don't have any more CPU left on this cluster. So obviously, this job is CPU bound. Adding more CPU is going to make it run faster. This is memory over here. So this isn't actually 0 on this axis, it's like 160 gigabytes. So you can see that we're actually really good on memory. We're not using much at all. So adding memory, it's not going to help at all. Now imagine if you had to do this on a busy cluster that was running a ton of jobs at once. You'd have no idea what your constraint was or why your job is running slow. But for us, it's completely easy because of this isolation. The other really important thing from running lots of clusters is that our data scientists and our data engineers and our automated jobs don't have to wait to do their work. You can get the cluster you want, and if it's going too slow, you just scale it up to make it go faster. So we can basically optimize for the amount of time that we want a job to take rather than for anything else. This is really important for us because we want our employees to be able to move as fast as they can. The next thing that doing a cluster per job does is allows us to optimize really nicely by picking the right hardware for the job. So for instance, that job we saw before was CPU bound. Other jobs that we have are actually memory bound. They do certain computations that require a ton of RAM. So if you work with Amazon, they sell different types of instances, instance families, and each of those optimize for something different. So the C3 instance family at Amazon optimizes for compute. If you buy one of these instances, it'll give you proportionally more CPU and less RAM for the same price. Whereas if you buy one of the R3 family of instances, you'll get more memory and less CPU for the same price. So what we'll do is actually pick the right instance type for the job, and in practice you save about 30% over buying just general hardware, which is really nice. We also use M1X large a lot if you don't care about what's going on, if it's just a job that needs to run and run whenever, because they're dirt cheap and Amazon has a ton of them. Another super surprising thing that we do, and that we can do because we have so many clusters running, is run 100% on spot instances almost all of the time. So if you're not familiar with the spot market, in order to serve the capacity of all of their users, Amazon has to have a lot of extra servers sitting around that they're not using. What they do is make these available for purchase at discount on the spot market. So you make a bid and you say, I'll pay this much for an instance. Maybe I'll pay 50 cents. And if the spot price for that instance is under that, if it's 10 cents, you'll get the instance. But if the spot price goes up above your bid, you'll lose it. So what this means in practice for us is two things. First, we have ridiculous savings that we get by using this market. And second, our clusters can disappear at any moment. So a little bit more detail about how we do this. So we suck all of the data about the spot market into Datadog, and we use that for visualization. What you're seeing here is a visualization of the spot price for C3 2x large instances in the US East 1 region. Each of these little lines is an availability zone in that region and the current price at that time. So you can see that the price is roughly around 10 cents, which is what you pay per hour. We start by bidding the on-demand price, which is the little line you see there between the green and red, which is 42 cents. So here we would be good in any availability zone. We'd get capacity, and instead of paying the 42 cents, we would pay just 10 cents. But sometimes things get a little hairy, and you have to fall back to on-demand if the prices go high. So we automatically do that. If we're having trouble getting spot capacity, our clusters will fall back to on-demand. And because of this, you pretty much have to monitor everything you're doing, all of your jobs, all of your clusters, and the spot market as well. But the upshot is you can save 80% over the on-demand price if you do that, which is an enormous, enormous savings. If you couple that with optimizing for hardware, it's truly, truly amazing. It sort of gets you back down into the realm of bare metal pricing and opens up a lot of new use cases that you can do. A little bit more about monitoring the spot price. This is an example of the opposite behavior that we saw in the last graph, where all of the availability zones are really, really highly priced and are above our bid. When this happens, we're not only going to lose our clusters that are running, we're also going to be unable to get new capacity. So we would automatically switch to on-demand, but here there's an optimization. Whenever we see that all of the markets are above price, we'll actually page an on-call engineer, and all of our most important jobs are tuned to be able to work on 2 different types of hardware class. So we can switch out of this market, which is volatile and not very conducive to savings, and switch to a secondary instance type, where we can get better prices. This is a pretty nice way to deal with sort of short bursts of spikes across an instance type. So this may all sound crazy, but it works really well. So in practice, you don't have to wait for a cluster anymore. You wait maybe 5-10 minutes if you need to launch one, and then it's yours to do what you need. And when you're done with it, you can just shut it down. There's no waste from hardware sitting around. And the difference in price from the spot market opens up all sorts of new use cases that we can do on clusters because they're so much cheaper. But it doesn't all come for free. There's stuff that we have to deal with. And most of that is around the fact that we have many things now and they go poof. So that brings me to the third section of the talk, which is the copious tooling that we have to put around the edges to actually make this work. So first off, we have a hub where we're sort of collecting all this tooling, which is a big data platform as a service that our internal users can access. This is called Mortar, and it does a lot of things: jobs, clusters, schedules, users, what have you. I'm going to focus mostly on the ones that deal with elasticity, since I don't have time to discuss everything. So the way a user at Datadog would work with this is they have 2 interfaces. One is a command line tool, and one is a website. The command line tool lets them check out their code locally, do development there, and then when they're ready to run it or test it on a cluster, they can say, please run this Spark job in this environment with all of these parameters, or run this Luigi job, what have you. It'll package up the code, send it in, and start it running. And then on the website, they get to see all the logs, visualizations, links to the clusters, pretty much everything that's going on in real time. So the architecture of this builds on what I showed earlier, where we have our data stored in Amazon S3. On top of that, we layer Elastic MapReduce, which is Amazon's Hadoop and Spark as a service product. Elastic MapReduce is giving us a lot of nice things out of the box. So it launches clusters for us, it stops clusters when we're done with them, it provisions software onto them, it makes it really easy to add nodes and take them away, and it also deals with the spot market. So you can do spot pricing and it'll take care of that. One more subtle thing that you might not realize about Elastic MapReduce, if you haven't worked with it before, is that it has a highly superior file system for accessing files from Amazon S3 to what's available in open source. So it's much more reliable, it's much faster. And this is a big benefit of using EMR. There's some work underway to work on the S3A file system to make it better, but right now EMR has the best. On top of that, we layer a sort of worker layer that are responsible for the main programs we run. So they're pig workers. They actually do quite a bit. They're running the pig job, interacting with the cluster and making sure that things are good, sending logs back to us where we can see them in our interface. And then Spark workers, which actually do a lot less. So in Spark, we just compile the code, we send it into the cluster, into Yarn, and we run it there with Spark on Yarn in cluster mode, so it's actually executing inside the cluster. For Luigi, that's actually doing all of our sort of task and workflow management, and those are running all the time to make sure that things are doing what they're supposed to. Up a layer from that, we have to store a lot of data about what's actually going on in the system so that we can query it very quickly. There's a metadata DB that's got like all the clusters, all the jobs, what their current state is. Also a queuing system because we have lots of long-running things here where we want to put jobs to our workers and have them do it, and then as many logs as we can collect. On top of that, the website and the API, and then finally the CLI and the clients that are accessing it, and then a job scheduler, which is sort of, it's like a human using the system, but on a more predictable schedule. And finally, we're sending monitoring data for all of this into Datadog so that we can see what's going on. So some questions that we like to think about and answer with this tooling. The first tricky question is, we have all these clusters, they're coming up and down. How do we actually find the right one, and how do we deal with them disappearing? Our answer for that is tagging our clusters. So each of our clusters gets a tag which tells you what it's doing. So for instance, this cluster might be the monitor report cluster, it's tagged with that. The other one may be something that's doing anomaly detection. And so what we can do with that is whenever we go to launch a job, we ask the platform to run it on the monitor report cluster. And what the platform will do is go find this cluster if it exists and run the job there, but if not, it'll start it up and get it ready. And this is really good for dealing with spot instance failures, because it means that if the cluster has gone down because the spot instances were reaped or something like that, it'll just restart it and it'll be right back where you need it. So all you have to think about as a user who wants to work with a cluster is, what do I want to call it, and is anyone else using that name? So another thing that we have to think about is, how do we actually monitor all this stuff? How do we deal with the fact that these clusters disappear? And this flows pretty naturally from the cluster tagging idea. What we do is, when we tag all of our clusters, those tags go into Elastic MapReduce, and they also sync over to Amazon EC2. Once we have that, our monitoring tool, Datadog, can pull all of those tags in and put them on all of the metrics. So what that means is, for instance, this is a cluster monitoring dashboard. This is showing us the number of CPUs that are actually in use at any time on the cluster. I've tuned it to be the anomaly detection cluster. This little burst of activity could be on one set of hardware. We could have lost the cluster at this point and had to bring up a new one, a new spot instance cluster, but we'll see it with continuity here because they were both tagged the same thing. And we can choose that tag from up in a dropdown and say, please show me everything for it regardless of what hardware it was on. This is also super useful for monitoring, because it turns out that some of the clusters we have, we don't care if something bad happens to them. They're just development clusters, but others are very, very important production clusters. And we can set our monitors to be focused just on the tag that we want. So for instance, this monitor is saying that the anomaly detection cluster shouldn't run out of disk. So we're launching all these clusters. How do we actually avoid being overwhelmed by all of them, just growing amount of clusters? Well, we have several different ideas for how to deal with this. The first one is the simplest one. It's just, if you're going to run a job, have it shut off automatically when you're done. In practice, this doesn't work as well as you'd like. If you're a human working with a cluster, you're doing things iteratively, lots of things fail. Even automated jobs sometimes fail, and retries would make them work. So what we do more often is the idea of a persistent cluster. We have a monitor that's watching for whether there's any work happening on a cluster at any point, and we'll automatically shut it off after it's been idle for a certain amount of minutes. This is really good if you're doing some work and you want to leave it running while you go home. We'll just automatically shut it off for you. And finally, there's the old-fashioned permanent cluster where no one's going to shut it off for you. And these we keep ourselves safe by alerting on whether they're up for over 24 hours. A really big challenge then with many clusters running is, how do you actually debug problems when you have them and the cluster's gone? So there are a couple different things that we do. The most important, and so the base layer of this, is sending all your logs off of the cluster to S3. EMR will give you some of this for free. HDFS and Yarn it'll take care of. For any of the other things that you're working with, Pig, Spark, Luigi's on here too, you have to get all the application logs yourself and make sure that they arrive where you need them. But this is super essential because nothing's going to be around in the morning when you go to look for it. Logs are nice, but sometimes it's very difficult in a distributed system to piece together exactly what happened. So we have some visualizations that we run on top of that help. Lipstick shows us exactly what happened in any job. It keeps all the counters. It's sort of the visualization that I showed earlier. The Spark history server is a good version of this for Spark. You can actually submit all of your data there. We don't have that up and running yet. We're actually working on that now. And then we have a task flow visualization for Luigi, which shows us which tasks ran when and which ones failed. So that helps you sort of orient yourself into the logs so you're not just surfing through text. And finally, it's very, very important to preserve your monitoring data historically. When you have machines that are going up and down all the time, you need to be able to look back, like say, I want just the anomaly detection cluster and I want to see what it was doing for the last week, even when that hardware is gone. Something else that's really important is you need to make your job layer actually able to handle failure. For us, the answer for that is Luigi. Luigi is a workflow tool that Spotify open sourced a little bit ago. It's quite nice for this. The thing that Luigi does is allow you to take a very long, complicated pipeline of tasks that you want to do and split them up into small individual tasks. Each of those have a very simple semantics for how to make the task clean up after itself if it fails, and how to make sure that it can restart well. Also, each task knows how to detect whether it's already run and not do anything if that's happened. So this is a very simple example, just two tasks in a pipeline, A and B. Imagine that we have task A and then B depends on it. So if we run our pipeline and task A succeeds, it's good. But imagine that task B is running and the cluster that it's running on gets reclaimed for spot instances. So the task fails. What Luigi's going to do is actually clean up all of the partial data that may have been written by that task. And then we can just rerun the pipeline from the start with no additional parameters. And it's going to launch the cluster, run it again, and the job will succeed. This is really nice because it means that no human has to get involved when there's a failure. The property that does this is called idempotence, and it just means that you can just rerun jobs until they succeed or until you time out. So in practice, what this does is make small failures that happen all the time in our pipelines not have to elevate to the level of a human unless they're not resolving themselves. So to recap, we talked about the three different layers that we have in the platform. The cloud storage, where we keep all of our data in a way that's flexible, doesn't require a lot of management, and lets us point mini clusters at it. The elastic compute, where we're running mini clusters throughout the day using spot instances to make them very cheap, and allowing our data scientists and engineers as much capacity as they need. And finally, the tooling layer around the edges, which helps us deal with this level of dynamism and be able to manage it. So if you're just thinking about how to do your own cloud big data platform, or you have one that you want to sort of move forward, I have a couple recommendations for what you might look into. If you can, and you're in the cloud, you should definitely use S3 for your permanent data and not HDFS. This is actually applicable to many other clouds as well. Cloud storage is becoming fairly commoditized, so Azure and Google Cloud have very good options for this as well. If you're in Amazon, don't start building from EC2. Start from Elastic MapReduce if you can. It's going to give you a lot out of the box, and eventually if you need to rebuild those things, you can, but it's a great place to start. Even better, if you can, look into using one of the platforms as a service that are available. Netflix has an open source one called Genie. They're doing quite a bit of work on this to move it from V2 to V3 right now. But Qubole and Databricks also have very solid platforms. Databricks is more focused on Spark, and Qubole is pretty wide-ranging. We found that tagging is actually a really, really good way to make sure that all of these things that you'll use that go up and down are able to be tracked across time, and that your users don't have to think too hard about which hardware that they need to work on. And finally, make sure that you get a workflow tool that has failure baked in. Luigi is a really good one for this. Airflow is also really nice. Either of those are going to work very well for you. So that's my talk. Thanks a lot. And if you, like me, are very excited about these things and want to work on Spark and Hadoop and Kafka and all of this stuff with us, hit me up on Twitter or send me an email or hit our jobs board. We're always hiring. Thank you.